So let us start with a cartoon diagram, which all you may have been know. Just let us recap. Is that this is, we know that stars are formed from a nebula due to gravitational collapse of with different time scales, James time scale, and all those things. And there can be two possible scenarios. One is a normal star like our sun can form from this nebula and spend its life, most of the life time is some millions of years, by emitting electromagnetic waves. And then when the fuel which is propelling it, that means hydrogen and helium, burns, then for this type of stars like sun, they form a giant star which is known as red giant, where the innermost part is a carbon core, the outermost part are still hydrogen, but the thing is that they expand. And what happens is, from this stage they go on to have a planetary nebula, where the innermost part which remains, but the outermost part is scattered away by the planetary winds and all those things. And ultimately what we have, the bare core, which is the white dwarf. On the other hand, if you have a slightly massive stars than sun, let us say 4 or 5 times the mass of the sun, they also go into the main sequence, spend their life a relatively smaller lifetime than these stars, and ultimately when they are near their death, they become red supergiant. Red supergiant is much bigger than this red giant. The inner core is still is very almost iron, okay, and the outer core is again hydrogen. And then what happens is, the gravity then so for such stars, the gravity cannot still the pressure, the internal pressure cannot balance the gravity. What happens is, it forms a supernova. So, and once it forms a supernova, for let us say a star which is in the range of 7-8 solar masses, they form a neutron star, and much higher stars which are 10-15 solar masses form a black hole. So I will be spending much of the time in this talk in this neutron star scenario, and as you and why neutron star scenario can unravel the physics of high density matter, I will convince you. So let us go on to the next. What is the neutron star? Neutron star was first theorized by Bardet and Zwicky just after the discovery of neutron. Neutron was discovered in around 1930. Bardet and Zwicky then gave the prospect of having neutron stars, that means stars having a lot of neutrons, composed totally of neutrons, and they proposed it in 1934, just after 4 years, almost 3-4 years, just after the discovery of neutrons. And however, the connection of neutron star with pulsars happened almost more than 30 years later in 1967 by Hewish and Bell. So what are pulsars? These are the pulsars, is that they are rotating, they are rotating neutron stars. So this is the rotation axis and this is the magnetic axis of the stars. These stars are very have the strongest magnetic field that can be experienced in the universe. And from these magnetic poles, they have this electromagnetic emissions, which we see it in terms of pulses. Okay, so this, what is the mass range for these neutron stars? They are of 0.7 to 2.4 solar masses. 0.7 is the new discovery of Hess. Otherwise, it was theorized that they are above 1 solar mass, but the new neutron star Hess has put something new into it. It has a radius of 10 to 15 kilometers. Okay, and it has it rotates very fast, from starting from millisecond to seconds. Okay, it has a period, and we can see that because of this huge masses and confined within such a small radius, they have a density at the core which is of the order of 10 to the 14 to 15 gram per cc, which is, you can think of, is 6-7 times 10 times the nuclear saturation density. And the magnetic field calculated from this period and the pulses and their masses is of the order of 10 to the 15 to 16 Gausses, which is at the surface. So you can think of that because of this high density, that therefore this thing is very interesting for the particle physicist, but also it is interesting for the astrophysicist. So let us go back to just the theory to have a recap. So as you can see that neutron stars are such a compact object. So you can think of that they cannot be described by the normal Newtonian theory or the normal theory of hydrostatic equilibrium. What we can do is, it was first solved just after the in the early 90s, early 1900s, in the 20th century, by Tolman-Oppenheimer-Volkoff, where they solved this Einstein equation, taking a finite ideal fluid matter for the T mu nu, and they got this equation, which is, you can see, is a hydrostatic equation. This is the hydrostatic equation, and these are the corrections. This is the basically the generalistic collection. These are the relativistic collections of this hydrostatic equilibrium condition. So basically, this pressure balances. It says that the pressure balances this gravity, and therefore we have this structure. And there also we can have this mass formula, as you know, from the hydrostatic equilibrium. So how can we solve for this neutron stars? Is that we can start with certain energy density, okay? And if we have an equation of state, that is important. Now we need an equation of state. So let us say that we have equation of state which is connecting energy density with pressure. We can calculate the corresponding pressure, and from that pressure we can then solve this equation simultaneously, these two equations, and then we can solve for the next pressure point. Once we get the next pressure point, we know the equation of state, which is the connection between pressure and energy density. We can again find the energy density, and from this way we can iterate it continuously, and from the center to the surface we solve this equation. And when we have this pressure to be 0, we say that that is the point where we have reached the surface of the star. So this is the surface of the star. You can see the pressure or the energy density as 0, and the mass saturates. This is the 2 solar mass, around just above 2 solar mass. So we say that the star is around 14 kilometer and has a radius of has a mass of 2 solar mass. I have not considered. I will tell you what are the equation of state I will. So you have to consider some equation of state. This is done for some NL3 equation of state, but that is not the point. I will come to the point in the equation of state in the next slides. Okay, so this is how you do. So next, what you are asking is that given an equation of state, this thing solving that TOV equation is very trivial. Okay, and for a given equation of state, we can pick up this masses and this mass and this radius, okay, and point it. Let us say this is the equation of state I am talking about, and place it here. So it will have a point. This is the one point. Now we can change the central density, and then we will have different points, and we will get a curve. So for different central densities, we will have different mass radius curves, or this is called the mass radius sequence. For different equation of state, you see that these sequences are unique. So given an equation of state, we'll have this mass radius sequence. Okay, now the questions come is, what is the actual equation of state at that of the neutron star? What is the equation of state? Once we know the equation of state, everything follows. It is very simple. But what is the equation of state? The equation of state is the questions that we will be answering, we will be trying to figure out in this presentation. And if we know the actual equation of state, we will know the form of matter at the neutron star core, and then we can test the theory of high density matter, because this neutron star, this mass radius curve is an observational signature of that equation of state. So we can test the theory of high density matter with these observations. So we will be doing that in the next part of the talk. Okay, why this is again a pictorial equation is why this is very interesting is that as I was telling that this is the phase diagram of QCD. This is the temperature curve, temperature axis, and this is the chemical potential or the number density axis. And you can see that this at very low baryon chemical potential. This is the early universe picture, and here we have high temperature and low density, which is probed by the Earth-based experiments. And this part of the phase diagram is probed by the low density experiments. That is, some of it are working and some of it are yet to be started. The interesting thing is that this part has no experimental no experiment is going on for this part, because there are some problems both theoretically and experimentally. And so the only place where we can test these theories of equation of state or the QCD are the neutron stars. So therefore this observation and the physics of neutron star is both important to astrophysics and also to the particle physicist. And in the high temperature regime, what happens is this lattice QCD calculation has found out that the phase transition happens from the hadronic, this is the part of the hadronic degrees of freedom, and this is the part of the quark and gluon degrees of freedom. And lattice QCD has calculated and shown that this phase transition here from the hadronic degrees of freedom to quark and gluons is a crossover transition. Okay. However, people believe that if I go to the low density, high density or high chemical potential, low temperature part, we will have a first order phase transition, or at least some order of phase transition will be there. This is not a smooth crossover that we have seen, and we'll also experience a critical point here. So this is the part why this we are going into this picture of equation of state and neutron stars physics. So what is our present knowledge? So of this equation of state that I am talking about is that this is a pressure versus energy density curve. So we know fairly well this low density part from nuclear experiment and also from chiral effective field theory. Okay, chiral effective field theory is a field theory which takes into account the chirality of the account, and these are the degrees of freedom here is hadrons. And at very high density, we also have a good prescription from theory is the perturbative QCDs, and which works pretty well in high densities. Okay. However, in between this, we don't know what is the equation of state, and that is the challenge that we are going to tackle with astrophysics in this talk. Okay, and this patch is the central densities, maximum central densities that a neutron star can have. Okay, different neutron star, different equation of state will predict different maximum central densities. So there is it's not a line but a patch. Okay, so this is the current status, and this is where the theoretical calculation, basic theoretical calculation of particle physics and nuclear physics stops. And then what we have is, then in this talk I will show that how astrophysics takes over this. Okay, let us begin. So what we'll do is we'll try to construct an agnostic equation of state, a bunch of agnostic equation of state ensemble. Ensemble means I am talking about of the order of million. Okay, equation of state. What I will do is, so we have this thing which is known, right? This part of the equation of state is known. That means we know that c square, speed of sound, and this part of the equation of state is also known. This is from perturbative QCD, and c square we know is 1/3 here. Okay, and in between the c square can lie between 0 to 1, because this is the causality limit and this is the thermodynamic stability limit. So what we can do is we can randomly choose continuously for a single equation of state. We can randomly choose the different c square values, and once we have chosen c square values, we'll connect them with a piecewise linear extrapolation to generate a continuous curve, and then from the c square values we'll calculate from the c square values we also know the mu, because this is chosen with respect to mu, and from there we can calculate the number densities and the pressure. And we should always remember that for it to be thermodynamically consistent, the pressure has to be smooth, okay, and the chemical potential has to be smooth. So what we then do is for a particular choice of this 6 different c square, we get this points, and then we extrapolate it with a piecewise linear. We can also collect it with a piecewise polytrope and a polynomic or parabolic, and then we will get a smooth curve. So now this is for a one equation of state. We'll repeat this a million times. Once we repeat this a million times, what will happen is all this part will be filled, and we'll have all sorts of equation of state lying here. And what will happen is a region like this. So these are the all possible values that equation of state can have, but this is bounded by the thermodynamic stability and the value of the causality. So these are so our equation of state cannot lie anything outside this band. So we will get a thing that I have showed you. Now comes the astrophysical constant. Now comes the astrophysics. Is that we know that if I get a equation of state, then I can solve the TOV equation. I will get a single curve, right? I will set a single mass radius curve. Now, if I have for say 1 million equation of state, I will have all this mass radius curves. Now, what happens is, now comes the astrophysical constant. What are the constants? Are the different masses. That means we have seen pulsars of as high as this type of, as high as 2 solar masses, and this one is a much higher, which has a controversy, but let us say that masses are beyond 2 solar masses. So what happens is any equation of state which doesn't go on to and reach the 2 solar mass will be distracted. Okay, we will not take that into account. This is one of the constant. Another constant is the radius. For 1.1 solar mass, we have observed a radius of which has to be greater than 10.75 kilometers. So any equation of state which gives a radius less than of a 1.1 solar mass star less than this, we will discard that. So these are the different bounds which is shown here. This is, as we told, is a causality limit comes from the speed of sound. Here, this is for this green one, PSR. This is 65% confidence level. This is 93% confidence level. Okay, so these are this equation of state. These are the bounds that are given by the astrophysics. These two bounds are coming from the gravitational wave data that we have seen, GW170870. This is for M1 and this is for M2, and these are the bounds given by some other papers, which are a bit complicated. We will not discuss most of this, but these are the and this is the bound of the Hess. This one, this is the bound of the new solar star pulsar Hess. So any equation of state which we are building and has to be consistent has to satisfy all these constraints. And let us see what happens. So this initially, if I say that my neutron star is greater than 2 solar masses, so all this equation of state will satisfy them, and we'll have this type of curves. So you can see that this is a boundary. This is not a curve. This is a boundary. So therefore it is a very weird shape, because some equation of state is like this and gone on to this. Some equation of state has started from here and gone on to the smooth. And one interesting thing is that you can see that initially the equation of state has to be stiff, and then it can become smooth. Okay, not smooth, soft. These are all smooth. First it has to be a very stiff, and then it has to be soft. This is a characteristic which came out from this mass radius constant. So, and if I set a higher mass constant, this is, let us say it is 2.1. So this equation of state are not going to satisfy. So we'll have a green band here. Okay, so this region shrinks. As we go on to the higher masses, you can see that region shrinks. So our ultimate aim is to shrink this as far as possible and to find a unique equation of state, whatever unique we mean. And within but this are only till, let us say, in this band. It has to be only within this band, because this is the maximum central density of neutron star. We cannot control this type of here. The equation of state that is building here is here. But we can see that if this is constant, this will already be a bit constant by the previous constants here. So our aim is to do that. Okay, so so I have told you there are different ways of shrinking this. Different people are trying different ways. I will show the two ways. Which one way I will see is not successful, another way is successful, and there are many other ways I will talk into in this talk. So one way is having a universal relation. Universal relations are for the case of neutron stars, there is a three quantities which show some type of universal relation, which is the moment of inertia, the quadrupole moment, and the tidal deformability or the tidal love number. So it is called I love Q relations, which shows universal nature for neutron stars. So these are exactly not the moment of inertia, but it is normalized by some factors, and in this Q bar, I bar, and I will show that lambda bar will show some universal nature. But let us first start, and we will to have a quadrupole moment, we have to have a rotation. So we have chosen a rotation of a star of 450 hertz. We can choose any type of rotation starting from, say, not very low, that is from 50 hertz to 700 or 800 hertz, and you will find that this also satisfies the universal relation. Okay, so if I first plot this I bar, okay, against mass, you will see that there is no universal relation because there is a considerable spread, and you can see that the spread depends on the mass bound that we choose. Okay, so if I have a lower mass bound, everything will, there is this bigger spread. If I have a higher mass bound, the spread is much lesser. And there is also a similar spread if I plot Q bar as a function of mass So as a function of mass, you can see that these are the spread. Okay, so this doesn't show I and Q doesn't show any universal relation with mass. However, if I now plot them as a function of lambda bar, you can see that we have a very good fit of a universal relation, a single curve, a single line, almost a line, and in this single line, everything sits there. So this is the universal nature that I'm talking about. So this has a curve with minimum spread. There is almost no spread here. It's like a single line, and this is true for I and also Q. And remember that we have plotted it as a function of lambda. So therefore, there is a universality in this parameter space I love Q. So now if I fit a line in these two cases and with this polynomial, okay, and then I have some values, and we can check that different there are other calculations which say that these are almost universal relation in nature. So how can I exploit the universal nature to differentiate equation of state? Yeah. So what happens is now we want to check how universal are the universal relation. So what we can say is that there was a very minimal spread. We want to check what is the spread there. So we have plot the fractional error of the between the fitted curve and the data as a function of lambda, and we can see that everything lies within, if we fit a tolerance limit of 5%, and everything lies within that tolerance limit. So any point which is in between this tolerance limit, we say that we satisfy the universal relation. So this is the tolerance limit that we have for defining our universal relation, right? Now, and we can see that it doesn't depend on the mass and anything, almost everything is universal. And but we can see that the lower mass stars are lower mass means higher lambda are more universal than the higher mass star that you can expect. But that is not a very big problem. So let us now check this universal relation to unravel the density. So what we do is we construct different kinds of equation of state. So the non-monotonous is that the equation of state that I have talked about is the yellow patch. So what happens is the speed of sound can go up, go down anywhere starting from the nuclear theory to the perturbative QCD, where it has to end at 1/3 value. Okay, so it can go up and down continuously many number of times, whatever. It can be non-monotonous anywhere. Okay. Next is we change our criteria and say that it has to be monotonous everywhere. That means it should be starting from here at very low density, and then it will increase, but it will not cross the perturbative QCD limit, which is 1/3, and from almost 0 to 1/3, it should be monotonous. So this is another criteria, and then we can have a bunch of equation of state satisfying this criteria. We can have a third branch, which is monotonous. The equation of state can be monotonous inside the neutron star, but outside means beyond the neutron star densities, it can come down. So these are the three different equation of state, and we want to check whether this equation of state also satisfies the how smooth is the universal relation for these three different types of equation of state. So this is the graph that we are obtained from this equation of state graph from the pressure as central density, and you can see that different equation of state has different ranges. The regions are very different, and we expect something. However, we were very we were interested, but it didn't satisfy our goal. And we said that all this, even with different equation of state, they were not lying. They were almost following the universal relation. So the universality still holds, and we can see that they are also satisfying the 5% tolerance limit that we have set our benchmark. So all the equation of state with different type of equation of state were all within the tolerance limit. So smooth equation of state, whatever may be, whatever our goal is, will holding this universal relation. So our universal relation to differentiate the equation of state failed. So however, the important thing is, that is what I have told you. The important thing is we are checking a family of equation of state, almost 1 million, which has a fast order phase transition. Till now we have checked with smooth equation of state, that means equation of state which doesn't have a very strong fast order phase transition. It can have a crossover or a smooth equation transition, but presently we are checking this thing with a equation of state with first order phase time. Before I end, I want to thank my group members, and these are the sites. If you want to look into our work, we can go and visit these sites. And saying that, I should thank you. Thank you for your patience. Hope you liked the talk.